Hello everyone, my name is Silvio. I will present to you this paper named A Graph-Based Feature Selection for Intrusion Detection in Cyber-Physical Systems Perception Layer. The other authors are Passos, Célio Albuquerque, Mossé, and Luiz Ochi. So cyber-physical systems already researched several industrial IoT systems, for example, manufacture and power industries, such as this figure that illustrates substation systems. And in these systems, security is very important, especially the resilience of such systems to attackers. And in the past recent years, many attacks were reported targeting the power systems, nuclear plants, airplanes, electrical vehicles, and other related domains. So to stop these malicious activities, it's very important to employ some intrusion detection systems. These systems play a crucial role in cyber physical system security, and the effectiveness of the systems depends on the detection, timing, and accuracy. And feature selection methods help to improve both goals. We can increase the detection accuracy by discarding irrelevant features or redundant ones, and as secondary benefit, we can reduce the feature subset. That means to have less data and faster processing to process all this data. So this work investigates how feature selection techniques may improve intrusion detection accuracy in the cyber physical systems, specifically in the cyber physical systems perception layer. So in particular, we propose a grasp-based meta-heuristic implementation for feature selection. I will talk about grasp in the next slides. So basically, these methods run offline to pre-select important features. For after this pre-selection, we perform the online IDS, intrusion detection system. And basically, the result reveals that our implementation outperforms the accuracy of traditional filter-based methods. I will talk about this in the next slides. And it's about to 17.25% on average of improvement by using grasp-based feature selection rather than filter-based traditional methods. So this is the big picture of a cyber physical system. We can divide it in three main layers. The first one is the physical world, and the third one is the cyber world. And between these layers, we have a transmission layer that is basically composed by transmission technologies to communicate data from physical or cyber worlds. And specifically in this physical world, we can have many smart objects that have devices such as sensors or actuators, and these devices are prone to a lot of attacks. In special, we will address three main attacks that can be launched to target this layer. These attacks are both variations of DOS or denial of service attacks. The first one is flooding. In flooding, basically the attack will send a large number of advertising cluster head messages. That's a typical message exchanged in the leech algorithm that is shown in this figure here, where we can have a lot of sensors, and these sensors send data to the CH, that's the cluster head, and each cluster head from each cluster will synchronize its data to the base station. So basically, each cluster will send a large number of messages to other clusters, to other sensors, to become a cluster head. And this is the flooding attack. This message will be sent in a high transmission rate and a large number of messages. After a malicious node become a cluster head, it can launch two other attacks that are black hole and gray hole. In the black hole attack, the attacker advertised itself as CH, as I told you before, and after became a CH or a cluster hole, it will drop all messages. So basically all the other sensor nodes will send it data to cluster head to it be sent to the base station. However, as it is an attacker, it will drop all the messages. So in the black hole, no messages are sent to the basic station. And similarly to this attack, the gray hole is also the CH is also compromised by an attacker, but instead of to drop all messages, some particular messages are selected to be sent to the base station. So if you employ an IDS, for example, at that place, we will verify that it's still receiving some messages from the other sensors, the legitimate sensors, but part of this message will be discarded by the cluster head. So talking about the detection methods, we can split all the detection methods in host-based or network-based methods, and we can also have different algorithms that can be employed to detect intrusions. So in our particular case, we will use both features from the host level or application level, and also network-based features that relates mainly in traffic features. So we will analyze both these features, and we will use 5 different classifier algorithms to detect when a sample it's represent an attack or benign activity. So talking about the related works, we have GRASP, our main related work. That's the iterative multi-start meta-heuristic proposed to solve graph planarization problems. But also after that, other works used this algorithm, the GRASP algorithm, to generalize it to solve another combinatorial problems. So feature selection can be considered a combinatorial optimization problem, and as well other similar problems, GRASP can be applied to solve it. So all these works does not they don't deal with intrusion detection in cyber physical systems, IoT, WSN, or in general intrusion detection in any other domain. They just perform feature selection, but to other domains. And there are another works, in particular this reference, that apply GRASP to intrusion detection context. However, they apply it to traditional networks that is different from cyber physical systems or WSN, wireless sensor network. So in this work, we perform an assessment of a GRASP-based implementation as a novel combination of RCL. I will talk about RCL that in the next slides, and we'll use a novel combination of RCL, classifier algorithms, and local search. So basically, we will use particular components to implement a new GRASP-based algorithm based on the traditional algorithm, but with a few new components. And we also explore a new domain, that is cyber physical perception layer. So this is in the green box is the GRASP algorithm, and we have two main phases in the algorithm. So we will run in many iterations these two phases, and the first phase is basically to construct a solution, and after this construction we will have a greedy solution, greedy feature selection or feature subset, and based on this initial solution we will perform a local search to try to improve this solution, that is to achieve a better solution or that have a better accuracy because accuracy is the main metric to evaluate the goodness of each solution. So in this yellow box we have the construction phase, and that is basically we will employ a filter based method, that is information gain or IG, and after employing this method we will rank all the features available to select the top 20 features, for example, or top n. This number of features to compose the RCL, that is restricted candidate list, can be parameterized. So after to have a list of the top ranked feature, we will select randomly some features from the RCL to compose an initial grid feature selection subset. So we can choose, for example, number 5 to the length of this feature subset. So from these 20 features, for example, we will iteratively select random features until compose a feature subset of 5 features. After that, we will use this generated solution in the other phase, that is local search, and in the local search we will perform some neighborhood algorithm to disturb the solution and derive similar ones, or that means to exploit the neighborhood. And basically we will perform in this case the bit flipped algorithm, that is randomly choose one feature from the RCL and put it in our feature subset solution, and also we will remove a current feature from the current solution, and we will keep the same cardinality of 5 features. So this is a better representation. It's a graphical representation of both construction phase and local search phase. We will start having an RCL, and after this RCL is generated by filter-based algorithm, we'll construct a random solution. We will evaluate that solution with some classifier. In our case, we will employ multiple classifiers, so we will run all this process multiple times to evaluate it. And after this evaluation, we will choose the best solution to compose our final solution of the grasp algorithm. So basically, after evaluating, we will verify if it is the best solution, and regardless the best solution, we will send it to the local search phase. So we will perform here some movements like I told before, exchanging features from RCL and the current solution to generate the neighbor solution from this neighborhood. We will evaluate these new solutions, and we will output the best solution after a predefined number of iterations. All this process also is run many times until we search a criteria that is a max number of iterations. So basically, to experiment this algorithm, we will set up a grasp implementation, and we define as maximum iteration the number 5th, and 22 local search iteration. So basically we will have 50 full iteration, and for each of these iteration we will have 20 local search iterations. And also we choose the RCL as the full available features, because the WSN dataset that we used in this experimentation already have just this number of features. So to avoid discard many features, we will keep all these features as the RCL algorithm, as the RCL features list. So our grasp algorithm will take all these features as initial RCL. So the size of feature was set to 5, and the final solution accordingly we will have 5 features. And as local search, we employ the bitfit algorithm that basically exchange features between the RCL and the current solution. So as a result, we can see that when we use the filter-based algorithm, information gain ratio, or on air, for example, we have a fixed feature selection for all the classifiers, because this technique does not consider which classifier will be used. So it's not the best choice, because as we can see here, when we use grasp for each classifier algorithm, there are different features selected to compose the best feature selection subset. So basically each number here represents a feature index, and the description of each feature are listed here. All these features are captured from the WSTN dataset. So as a result, we can see that for black hole attacks, GRASP enabled the classifiers to reach an accuracy of 99.99%. That's the most high accuracy. That is the first bar, compared to the on-air and IG and GR. That's information gain and gain ratio. So when we compare GRASP-based feature selection, we can see that the accuracy is significantly improved to black hole attacks. Regarding flooding attacks, we can see that GRASP is also never worse than IG, GR, or on-air feature selection. And finally, to gray hole attacks, we can see that the GRASP achieved an accuracy about 99.9% for all classified algorithms except to naive Bayes. As I told before, this attack can be considered the most challenging attack, because as the attacker perform selective discarding, it's the behavior of its attacks is harder than the black hole or flooding attacks to detect. So as conclusion, we can see that perception layer of cyber physical system and IoT systems have some tiny devices, and these devices are particularly susceptible to threat due to their strained constraints, and planning and designing of a secured CPS are important, but using IDS is essential, because in many times it's not possible to stop all the attacks before they occur. So we need to use some IDS to take some action when a new attack is occurring, and this attack may be not predicted at the planning and designing phases. So feature selection is very important. It's a very important approach to obtain accurate attack detection and a timely attack detection. Also, we quantified how GRASP-based feature selection implementation can improve the accuracy of 5 classifiers to detect black hole, gray hole, and floating attacks, targeting the cyber physical system, specifically the perception layer. So, in summary, we can see that GRASP was able to increase the detection for all attacks, up to 31.8 for black hole, 12.26 for gray hole, and 7.70 for flooding attacks. On average, it provided an increase of accuracy in about to 17.25%, more than other filter-based feature selection. So it's all. Thank you, and I will pass some slide with some reference, but in our paper we can see more details, and now I believe it's open to questions. Thank you.